Okay, so hello everybody again. In this video, I'll be talking more generally about how circuits behave when they're hooked up to time variable currents. Last time we talked a little bit about how inductors affect how currents can change with time, specifically in the case where you throw a switch which turns a current on or off, and that if you have an inductor in the circuit, which you almost always do, the current doesn't just stop automatically, it takes some time to change. This is one example of a time variable current, but there's another one which we often want to consider and which will be very relevant in the next section, which is the case of something called alternating current, which you've probably heard about. Alternating current is the kind of current you have running through your house. It is distinguished from direct current. Direct current is what a battery puts out. It basically produces a constant voltage, shown here in the green line, and a constant current, shown in this brownish line. This is what batteries do. They just put out a constant voltage and drive, after transit has been removed, a steady current. If you have something generated by things like, say, an electric generator or other sorts of things, you have alternating current. In alternating current systems, both the current and the voltage swing back and forth. This is some examples here. Again, what we're plotting are quantities as a function of time. So at the start, there's no voltage and no current. Then the voltage goes up, then it comes back down, becomes negative, then goes positive again. And it just repeats this over and over and over. And the current goes a similar way. The shapes of these curves are sines and cosine functions. And this is just the basic properties of what's typically called alternating current. And this kind of behavior is what's going to eventually lead us to understand how light works, because turns out light involves similar oscillations. But for this purpose, we just want to consider these sorts of alternating voltages and alternating currents in circuits. And before we get into that, we should just remind ourselves of some of the basic quantities involved when you have these alternating signals. The key things to remember, or the key parameters that define these things, are amplitudes and periods. The amplitude is basically the most positive or most negative of the voltage or the current. So the voltage goes up and down, but there's a maximum value it gets to. That is the amplitude of the voltage variations. The current swings back and forth. It also has an amplitude. So that's basically how much the current varies, and it's the maximum and minimum values of the current itself. Remember, current can be either positive or negative in this case. Voltage can either be positive or negative. And the current being positive or negative, what that means is whether the current's flowing one way around the circuit or the other way. Okay, so amplitude's one important parameter in this case. The other important parameter is the period, which is how long it takes to go up, down, and back. So how long it takes to do a complete cycle. That's generally denoted by a period, by a letter known as T for time. And you can see in this case, both the current and the voltage have the same period. And for these particular cases, we're going to assume that's the case. Now, instead of worrying about the period, which is the time it takes to cycle once, you can also consider some related quantities, which are the frequency or the angular frequency. Frequency is generally denoted with the letter F, and it's just 1 over the time period. So if you have a short period, you have a high frequency. If you have a low frequency, you have a long time period. Angular frequency is often designated with this, which is the Greek letter omega, and it is basically 2 pi over the period. This crops up just because of the way sines and cosines work. I'll try and minimize the use of it here, and we'll just discuss that. We'll see if that works in section 4. So these are the basic quantities. And what we want to know is how this voltage and this current relate to each other when the currents and voltages are oscillating this way. Now, the way that works depends on what elements are in the circuit. So to start off with, let's consider the one we've dealt with before. That is, we have an alternating voltage source, and we just put a resistor in the circuit. So we just have a voltage source, which oscillates back and forth, and we have a resistor. And we ask, what's the current flowing through the circuit, and what is the voltage across that resistor? Now, if we assume this resistor obeys Ohm's law, voltage is current times resistance, then what's nice is this is a pretty easy thing to calculate. The current and the voltage oscillate back and forth in sync with each other because at every given time, the voltage is the current times the resistance, or the current is the voltage over the resistance. What this means is the amplitude of the current variations are directly proportional to the amplitude of the voltage variations, and the constant of proportionality is this R. This is fairly straightforward. It's just an extension of what we've done before. Just that this means that at every single time, the current is just the voltage divided by R. This is a straightforward case for an ohmic resistor. And so this is why we can just still call this the resistance. What gets interesting is if we start considering things like inductors. Inductors don't work like this. Remember, inductors don't like having the current change. So it turns out if you put an oscillating voltage signal into an inductor, the voltage oscillates back and forth, and the current does oscillate back and forth, but they oscillate out of phase with each other. That is, when the voltage starts to switch from positive to negative, which would normally cause a change in current, the current actually remains kind of constant. So at that time, the current isn't changing, but the voltage is. Now, as the voltage continues to change, eventually the current does change, but it's out of step. So as the current starts to swing back, the voltage starts to go the other way and tries to push the current backwards again, producing another place where the voltage is changing rapidly, but the current is remaining negative. Now, this is a property of an inductor. So in this case, we no longer have voltage and current tracking each other, but they're both oscillating at the same frequency or with the same period. And it turns out the amplitude of the voltage variations and the amplitude of the current variations are still proportional to each other. It's just they're no longer determined by just the resistance. It's determined by something called the reactance. This is again because people who do electricity and magnetism have to name everything with cute names. Now, we should be careful here. This is no longer true that voltage and current are proportional to each other, because sometimes the current is big and the voltage is 0. Other times the voltage is big and the current is 0. But the amplitudes have a relationship. And also other metrics like what's called the RMS variation have a similar relationship. It turns out that the voltage is equal to the amplitude of the voltage variations is equal to the amplitude of the current variations times the reactance, which is generally designated with the letter X, with an L put after it to indicate it's due to an inductor. This works, this is not that different from Ohm's law, although it only applies to the amplitudes. And it turns out that this reactance is related to the inductance of the inductor. It turns out it's given by this formula here. The reactance of an inductor is 2 pi times the frequency of these voltage variations, or the frequency of the current variations, times the inductance. Remember, inductance has units of ohm seconds. So if we multiply that by frequency, which has units of 1/seconds, we get something with units of ohms. So this is the analog of Ohm's law for alternating currents with an inductor. And the important thing to note here is it doesn't care about the voltage amplitude or the current amplitude, but it does depend on the frequency of these signals. That's different from the resistors, which don't. Okay, so that's the basic idea. That's a way an inductor is different, and it's because the inductor reacts to changes in current, not to current itself. Okay, so we're going to do a couple of quick example conceptual problems here. I would suggest that you pause the video after I give one of these so that you can actually see what you think about it before you just see the answer. Whether you do or not, that's up to you. So what we're going to consider here is a couple of different signals going through this circuit. And we're going to ask things about those different signals. In particular, how this reactance behaves and how this current behaves. So first of all, we have a circuit like this, and we're going to have a voltage source which puts out a certain amplitude of voltage at some frequency. Which of the following AC signals will cause the inductor to have the largest reactance? Option A is a signal with an amplitude of 1 volt and a frequency of 10 hertz. B is a signal with an amplitude of 10 volts and a frequency of 10 hertz. Or C, both of the above signals give the same reactance. So pause this for a second and pick one of the answers. Okay? The answer is actually C. The reactance doesn't care about the amplitude of the voltage. It's just, so the reactance in both of these cases are the same. Now consider a slightly different situation. Again, which of these cases does the inductor have the most reactance? Is it when you have a signal with an amplitude of 10 volts and a frequency of 1 hertz? Is it when you have a signal with an amplitude of 10 volts and a frequency of 10 hertz? Or do both of these have the same reactance? This time, the answer is B. The thing is, if you have a signal with a higher frequency, so it oscillates faster, this inductor has a bigger reactance to it. Okay. The thing to understand is, what does this have for implications on the current? So again, if we have these same situations, but now ask which one produces the higher current going through the inductor in terms of amplitude, which of these has the larger amplitude current swings going through it? A signal with an amplitude of 10 volts and a frequency of 1 hertz, a signal with an amplitude of 10 volts and a frequency of 10 hertz, or they both give the same current? In this case, the answer is A. Remember, the current amplitude is the voltage amplitude divided by the reactance. I equals V over X. Since X is bigger for this case, you will get a lower current. So an inductor yields much higher currents when the frequencies are low. Again, that should make sense. Inductors don't do anything unless the currents are changing. So the faster they're changing, the more it does, the more it impedes the flow of current. So in general, the higher the frequency or the shorter the period, the bigger the reaction and the less current that will flow through an inductor. So that's nice. And is one way that this differs from a resistor. Now, there's one other type of circuit element we can discuss in this context, and that is a capacitor. We talked about capacitors in section 1. All it is two plates of metal separated by a gap. Now, if you hook up a capacitor to a DC voltage source, that battery puts charges on one side and not the other, and puts positive charges on one side and negative charges on the other, and just sets up a voltage across it. But what if we have an alternating voltage supply? Well, it turns out that if we have an alternating voltage supply, which is basically putting positive charges on one plate, then pulling them off and putting them on the other plate, and putting them on the one plate and then moving them off to the other, the current again gets pulled out of phase with the voltage, but in the opposite direction. In this case, if you put a lot of voltage across this thing, you will start to move charges. So if you start moving charges from one to the other, you have a big current, but not necessarily a big voltage across the capacitor. Other times when you're swinging through the current going the other way, you are now moving all the negative charges onto the opposite plate, which means the voltage across the plate is relatively small. And again, you get a similar sort of behavior. You oscillate back, and the charges are oscillating back and forth, and the voltage across this plate is oscillating back and forth, but they're out of phase with each other. So again, this isn't like Ohm's law. Volts and current are not proportional to each other, but their amplitudes are. So the amplitude of the voltage variations, V naught, and the amplitude of the current variations, I naught, are again proportional to each other, and the constant of proportionality is again called the reactance. This is, in this case, the capacitive reactance, so there's a little C there, but again, it's indicated with the letter X. Now, it turns out in this case, the reactance doesn't go like 2 pi times F times C, it goes like 1 over 2 pi F times the capacitance. This is completely orthogonal to how inductors work. And hopefully that makes some amount of sense. Remember, if you have currents that are not changing, an inductor doesn't do anything. But if you have currents that are not changing and you put a capacitor here, what will happen is the charge on the two plates will just get bigger and bigger and bigger until either the capacitor breaks or the power supply breaks. The capacitor is basically an open circuit, a break in the circuit for low frequency signals. If the frequency is high, if the frequency is low, the reactance is high. So we can see conceptual problems that try to test this. Let's say we're going to put an alternating voltage across a capacitor. in which case will the reactance be higher? We have case A, where a signal has where the voltage supply puts out a 10 volt amplitude signal and a frequency of 1 hertz. B is a signal with an amplitude of 10 volts and a frequency of 10 hertz, which gives the higher reactance. In this case, this one gives the higher reactance, case A. In case A, this thing acts more like an open circuit, so it has a higher reactance, just because this goes inversely proportional to the frequency. And again, which case gives you higher currents? Is it when you have a signal with a frequency of 1 hertz, a signal with a frequency of 10 hertz, or do they give the same value? In this case, the answer is B. Because if we make the frequency smaller, then the reactance is higher. But if the reactance is higher and we're keeping this amplitude of the voltage the same, the current needs to go down. Again, the way to think about this, if you have a very long period or a very low value of F, the reactance of a capacitor gets big. Basically, a capacitor with things that are very slow acts like an open circuit, like a brake. It acts like something with infinite resistance. If you have something that's changing the direction of the voltage really quickly, and so taking the current and sloshing it back and forth fast, then the capacitor doesn't look like anything. And it acts like an open circuit. So capacitors don't do much if the current is changing quickly, which makes them the opposite of inductors. Inductors don't do anything if the current is changing slowly. Capacitors don't do anything if the current is changing. Capacitors don't do anything if the current is changing quickly. And in general, the larger the frequency, the shorter the period, the smaller the reactance, and the more current flows through the capacitor. Apologize, I'll fix that typo later. So in general, if you have resistors, inductors, and capacitors, the way these circuits respond to voltage sources and what kind of way the energy and voltage is distributed depends on frequency. If you have something that just has a capacitor in it, then DC currents can't flow because there's no way for current to flow from one side of the capacitor to the other. You can only get current oscillating around in this thing if it's at a high frequency. This means that if you're sending signals through, only ones with high frequencies can get through. This thing filters out low frequency signal and is called a high pass filter. On the other hand, if you have an inductor and remove the capacitor, the inductor does not like the current to change quickly. So if you try and have a very fast current oscillation, the inductor won't let it happen. So high frequency signals get suppressed. Low frequency signals can go through fine. This is a low pass filter. And combinations can give you different combinations. Now, the last thing I want to mention briefly is what happens if you wire up both a capacitor and an inductor in a single circuit. What's neat here is this circuit actually will tend to oscillate on its own. Imagine we hooked this up and had some amount of positive charge on one side of the capacitor and negative charges on the other. Well, those positive charges and negative charges attract each other, and the wire provides them a way to find each other. So The positive charges would run around the wire in one direction, the negative charges would run around in the other. If nothing else happened, they would basically go around, neutralize each other, and the charge would be gone. But in this circuit, there's an inductor. As these things start to flow, they cause a current to appear. And the inductor doesn't want that current to change because it sets up a magnetic field. So after the two plates have neutralized each other, at that moment, there's a current flowing through this as the positive charges are moving through to where the negative charges were, or vice versa. Since this inductor doesn't want that current to change, that current continues to exist after the plates are neutralized, which means the positive charges overshoot and start collecting on the opposite plate. The negative charges overshoot and start collecting on this plate. The capacitor begins to charge up again, thanks to this inductor. Now, as the current stabilizes and goes back to zero, the inductor stops doing anything, but now the capacitor is back up and charged. And then those currents will start to flow back again, causing the inductor to activate. And so if you had no resistance in this wire, this would go on forever. The charges would just basically slosh back and forth between the two plates. And they do so at a very specific frequency, which is given by this formula here. It's just 1 over 2 pi times the square root of the inductor's inductance times the capacitor's capacitance. What this means is this circuit, just from two elements, will produce an alternating current with a well-defined frequency. This means this sort of circuit generates oscillating currents very well. It also turns out to be very sensitive to those sorts of currents. If you basically try to send a current oscillating at this frequency into a circuit like this, it will happily respond and start oscillating. If you send in the wrong frequency, it doesn't do too much. This turns out to be how circuits can be made to respond to particular radio signals, which occur at particular frequencies. And this is, in fact, how you can generate radio signals using circuits like this without having to worry about tuning the frequency. You've created something that has a particular frequency. Now, all of this discussion about frequency is meant to be preparatory for the next section of the course where it's going to become critical. Because what it turns out is oscillations like this don't just happen when you have circuits made out of inductors and capacitors and other things. They occur naturally. And those sorts of oscillations are responsible for making light. That'll be the subject of the next section of this course. Thank you very much for your attention.